So the first thing that you do, right? And I want you to observe this, okay? You have to not just rely on what you have done on your homework to do your term test or exam question. Okay, you can. I'm pretty sure a lot of you work really hard, and you could remember where the maximum uh or point is, and you cannot make a guess. Oh, it's going to be at point B also. No. Okay, you have to check. Okay, it's not like, okay, vertically it's at point B, horizontally also point B. Okay, I don't know. Okay, the thing is you have to check. Okay, so we are going to design the shear flow again, right? Okay, so point A and point B are still thin wall. Point A is thick wall. Okay, so we know that we have our terminal. Okay, so now we know that the axis that the first moment of area is going to take from is this axis over here. Okay, so this is our y axis now. Okay, so let's do some analysis. Okay, so if we look at points, you have your point A, point B, and point C. Now the thickness is different. Point A is 60 millimeters. Point B is 20 millimeters. And point C is 10 millimeters. So if you look at what we had before, right? Point B and C, the thickness is the same, but point A from 120 dropped to what? Dropped to 60. Okay. What this will do, you cannot guess. We are engineers. We have to have numerical values. You cannot say, okay, point B is still no. You can't just guess like that. Okay. So I'm going to find the first moment of area at point C first. And I know that this is equal to 30. Right? Let me again over at this stage, the geometries are critical. Okay, you get it wrong, we are game over. So this is 30. So we are going to find QY now at point C. Okay. The width is going to be equal to 10. The depth is going to be 30. The Y bar is going to be 30 divided by 2 plus, because this is 120, so from here to here is 60. Okay. We're going to add a 10. Okay, so let me check again. The width is 10, the depth is 30, the Y bar is 30 divided by 2 plus by 10. I'm okay. So this is equal to 30 divided by 2 plus 10 times by 30 times by 10 is equal to 7.5 times 10 to the power 3 millimeter cube. Let me do it. 30 divided by 2 plus 10 times by 10 times by 30. Good. Okay. Next, I'm going to do QY at point B. Okay. So QY at point B I will highlight to you, we are going to include this area over here, right, at point B. So we have to include 7.5 times 10 to the power 3. The width is 50. The depth is 20. The y bar is 60 minus by 20 divided by 2. Let me check 60. Yep, 20 divided by 2. Good. Okay. So this will be equal to 7.5 times 10 to the power 3 plus 60 minus by 10 times by 20 times by 50 is equal to 50 times 10 to the power 3. No. Let me 60 minus 10 times by 20 times by 50. 50 times. Okay, so this will be equal to 7.5 plus by 50 is equal to 57.5 times 10 to the power 3 millimeter cube. And then finally, we're going to do QZ at point A. Okay, so QZ at point A is thick wall analysis. So the area we're going to take is this whole area that we're going to take. Yeah, we have to consider this whole area now. So when that's the case, you have twice 57.5 times 10 to the power 3 plus by the width is equal to 60. The depth is also 60. The y bar is equal to 60 divided by 2, right? So this is equal to 2 times by 57.5 power 3, 11.5, 115 times 10 to the power 3, plus by 60 times 60 times 60 divided by 2, 108. Okay, 60 power 3 divided by 2, 108. So this will be equal to 115 plus a 108 is equal to 223 times 10 to the power 3 millimeter cube. Okay. So now we consider point A, right? And we're going to do the QZ over QY. So this will be equal to 223 times 10 to the power minus 6. Thickness now is 60 millimeters. Okay, so 223 power 3 divided by 60 power 223 power minus 6 divided by 60 power minus 3 is equal to 3.71 times 10 to the power minus 3. Let me do it again. 223 power minus 6 divided by 60 power minus 3. Yep, 371.6 times 10 to the power minus 3. At point B, QY over T. So at point B is 57.5 times 10 to the power minus 6. Now the thickness changes to 20 millimeters. So 57.5 power minus 6 divided by 20 power minus 3. Now this is equal to 2.875. Okay, now this is lower now. Can you see that now? Okay, it's lower than point A. And then finally, point C, the QY over T. So this is at what? 7.5 times 10 to the power minus 6 divided by 10. That's the thickness. So 7.5 power minus 6 divided by 10. So it's equal to 750. 7.5 power minus 6 divided by 10 power minus 3 is equal to 0.75 times 10 to the power minus 3. So from here, we realize that tau max will occur now at point A. No more at point B. After we change the direction from Vy to Vz. Okay. So with this, again, the same thing applies. So tau max is equal to 75 times 10 to the power 6. Okay. Which is equal to shear stress at point A, which is equal to V over I multiplied by 3.716 times 10 to the power minus 3. So the V over I ratio, which is constant regardless of the points that you take, is 75 times 10 to the power 6 divided by 3.716 times 10 to the power minus 3. Okay, so 75, 3.716 power minus 3 is equal to 20.183 times 10 to the power 9. Okay, so let me do it again. 20.183. Okay. So from here, we know that shear stress at point B will be equal to 20.183. Okay, 183 times 10 to the power 9 multiply by 2.875 times 10 to the power minus 3. So 20.183 power 9 times 2.875 power minus 3 is equal to 58.026 times 10 to the power 6 Pascal. 20.183 power 9 times 2. Yep, 58.0. And then at point C is equal to 0.75. No, 20.813 or 183 times 10 to the power 9 multiplied by 0.75 times by 10 to the power minus 3. Okay, 3.183 power 9 times 0.75 power 9 is equal to 15.137 times 10 to the power 6 Pascal. 20.183 power. Yep. Okay. So you can see just by changing the applied force, okay, the where tau max occur also changes. Okay, so you need to know how to analyze. So this example is unique because it combines both thin wall and thick wall analysis. Okay, take a 10 minutes break. We come back and we continue.